Welcome to this video about Coulomb's law. In this video I will explain to you the most important things to know about charges and the Coulomb force. Let's start by looking at a particle. Every particle has a property called charge, which can be zero, then we talk about a neutral particle. It can be positive, then it's positively charged, or it can be negative, then it's negatively charged. Every time you have two charged particles, there will be a force between them. The force between the particles is called the Coulomb force, and we can describe it with Coulomb's law. And we only need three things to describe the force: the charge of particle 1, Q1, the charge of particle 2, Q2, and the distance r between them. Let's take a look at the formula. On the left side of the formula we have an F. The F stands for Coulomb's force that we want to calculate. The first thing on the right side is a constant. We can ignore the constant for now, I will explain it later. And the last part is what we just discussed: the charge of particle 1, the charge of particle 2, and the distance r between them. Let's do a quick example so that you really understand the formula. We will imagine two charges with a distance of 2 meters from each other. The first particle has a charge of 2 Coulomb, and the second particle a charge of 3 Coulomb. Coulomb is the unit for measuring charges. We can now simply plug these values into our formula. Now there are two more things that we need. The first thing is epsilon naught, which is called the vacuum permittivity. You can look up its value online. And the second constant is pi, which you probably already know, but you can also look it up online. Now if we plug everything into our formula, we get our resulting force. The resulting force is here 13.5 giganewton. Now let's see what happens if we change our charges a little bit. So if we increase our first charge, you will see that our result increases as well. If we increase our second charge, the same will happen. Our result will increase. So we can note that a larger charge results in a larger force. But if we increase our distance, the result falls off rapidly. And this is due to the r squared in the denominator. So we can also note that the force decreases rapidly with the distance r. I now want to show you the force over distance diagram. On the y-axis we have the strength of the force F, and on the x-axis we have the distance r. What we can see in this diagram is how the force falls off as we increase the distance between the two particles. So this diagram is a nice way to visualize how fast the force is decreasing when you move the two particles away from each other. Let us now compare Coulomb's law with Newton's law of gravity, because they are both very similar. Both of them start with a constant. Then in Coulomb's law we multiply the charges and divide by the distance squared. And in Newton's law we multiply the two masses and divide by the distance squared. So the forces are very similar, and this might help you remember both of the formulas. Let's do a quick summary of what we know so far. If we have two charged particles, then they will interact with a force. The force will grow larger the larger the charges of the particles are, and will get smaller if they are further apart. A nice way to show the impact of the distance is with the help of this diagram. And the last thing we noted was that Coulomb's law looks a lot like Newton's law of gravity. This connection might help you to remember what Coulomb's law looks like. Now, how do you know that Coulomb's law is correct? And for that you can do some really simple experiments. The first thing that we can do is double the first charge. And we can see that the resulting force also doubles. And of course the same thing happens if we double the second charge. The force will double as well. By doing these experiments we can discover that F is proportional to Q1 and Q2. Now if we increase the distance, we will here see that the force decreases with a factor of 1/4. And if we increase the distance to 3 meters, we will see that the force gets smaller by a factor of 1/9. And just by doing these kinds of experiments, you will figure out that the force has to be proportional to Q1 times Q2 divided by r squared. Now, something you're going to find out if you're doing these experiments is that if the charges are both 1 Coulomb and the distance is 1 meter, then the result won't be 1 Newton. And instead the result will be something like 8.98 times 10 to the power of 9 Newton. And you will see by doing more experiments that this is just a conversion factor, which we will multiply with the rest of our formula. That we get this strange number has something to do with how 1 Newton is defined. Now the logical next question is, why don't we just call the constant a? Why do we have to say 1 over 4 pi epsilon naught? And the simple answer is, we will need epsilon naught later again. But if you rearrange the formula, you might see why epsilon naught is the more natural choice here. Because we divide now by 4 pi r squared. And 4 pi r squared is the surface area of a sphere. And you can imagine a light source, where light shines evenly in all directions. Then you will notice that the further you go away, the dimmer the light gets, because the sphere the light has to cover gets bigger and bigger. In the same way this light has to cover more and more room, the Coulomb force also has to cover more and more room in our example. So it makes sense that it decreases with the surface area of a sphere. Now, we haven't yet talked about what's the difference between positive and negative charges. And it's quite simple. If we have two charges of the same type, so two positive charges or two negative charges, then these two charges will repel. You can remember similar repels. And if we have two opposite charges, so one positive and one negative charge, or the other way around, one negative charge and one positive charge, then they will attract each other. You can remember opposites attract. Now, when we have a negative charge, then we can just plug in the negative value into our formula, and we can see that if we have only one negative charge, our result will be negative as well. And if we have two negative charges, the minus signs will cancel and we get a positive result. So a positive result tells us that we have repulsion, and a negative result tells us that we have attraction. The last thing I want to cover in this video is what happens if you have a positive charge and a negative charge and you are very far away from these two particles. Then what will happen is that they will behave as if they are neutral. So a positive charge and a negative charge, if they have the same amount of charge, will cancel each other out. And this also explains why our result was so huge, because our result was 13.5 giganewton, and that would be an extremely strong force for two particles. And the reason is that you can't make large charges, because if you have two positive charges, they will repel each other and instead attract negative charges. That's the reason why we normally only put very small things into the formula, and then our result is small as well. And that charges cancel is also the reason why most objects around you will behave as if they are neutral, even though they consist of very small charges. So let's do a quick summary. You have learned in this video what Coulomb's law looks like and that it describes the interaction between two charged particles. And you have learned that it increases with a larger charge and it decreases with a larger distance. And it decreases very fast with a larger distance because we have 1 over r squared. And what you also should know is that similar charges repel and opposites attract. And a negative result implies attraction in our formula if we want to calculate something. I hope you have a nice day and enjoyed this video, and thank you so much for watching.